the angular impulse and angular momentum, right? So we have seen a linear impulse and a linear momentum. We identify the symbol for it for uh, linear impulse. We have this force time uh, multiplied with a period of time, and then we have the linear momentum given by the variable g, right? Next, we look at the angular impulse and angular momentum. We start with looking at the motion, curvilinear motion of a particle in space, in three-dimensional space, defined by the rectangular coordinate system. We are using the same symbol that we had before when we consider the linear impulse and linear momentum. Additional information that we can see here is uh, the variable with the symbol h naught, right? So that is called angular momentum. H naught is the angular momentum, and this one is equal to the cross product of position vector times the linear momentum. So the cross product provide a plane A, right? So the vectors, so what it means here is that the angular momentum h about 0 there, O there, is directed perpendicular to the area created by this cross product of a position vector and the linear momentum. This symbol that I mentioned to you before, the angular momentum, can be quantified by the cross product of position vector with the linear momentum that the particle have, right? Actually, it's the moment of the linear momentum g about the origin. So we need to identify the origin. We need, because this value is also a vector quantity, right? So the first step when we try to solve the problem is to identify the coordinate system, right? Next is the definition on how we can evaluate the uh, the cross product. We can write in two forms, right? The first one with that expression, mass times the velocity in z direction times the position vector in y direction, and so on. Right. The next one is using the matrix, the symbol with the determinant there. Right. It's kind of like a determinant symbol there, and the constant for that matrix will be the mass of the system. So the angular momentum can be written in three forms there, right? So the moment of linear momentum, g about the origin, is defined by the angular momentum h of particle p about o. The angular momentum is a vector perpendicular to the plane A created by the position vector and the linear momentum. So when we say about the moment of linear momentum about O, actually it's a linear momentum of the particles times the moment arm r sine theta, or simply maybe r sine theta, right? It's mentioned, I shown in the figure there. So yeah, they are using a right hand rules, right? So we have right hand rule there. So it's only counterclockwise. So if you follow the method I suggest, And looking at the kinematics of motion is easy for you to remember. And then the unit for the angular momentum will be kilogram meter power of 2 divided by second or Newton meter second. Now we look at the angular impulse, right? So in order for us to look at the linear impulse, we look at the rate of change of angular momentum. So the reason why the author, Professor Merriam, introduced this topic is to relate the moment of force acting on the particle to its angular momentum. Angular momentum actually is the moment of linear momentum of particle about a center of mass, right? A center of location of the origin, right? So this is what we understood. And the moment of uh, forces acting on the particles about the origin is given by the summation of all moment about the origin is equal to the cross product of position vector with the all force summation of all force vectors there. And D is equal to the position vector times the linear momentum. So that give us the moment about origin. And D is the definition that we obtain, right? So the summation of moment actually is equal to the time rate of change of angular momentum. The moment about the fixed point O of all forces acting on the particle M with the mass M is equal to rate of change of angular momentum of the particle about O. And this is a vector quantity, and if you are using the rectangular coordinate system, we can write this equation in terms in the form of equation 332. So the moment of forces acting on particle P actually represent the instantaneous relationship between the moment of forces with the time rate of change of angular momentum. Now we look at the angular impulse momentum principle. Right? Previously, we have a linear impulse momentum principle that lead us to understand about the linear impulse. So using the same approach, the author look at the effect of moment of forces on particle on the angular momentum of the particle over a finite period of time. So the unit of angular impulse is Newton meter second or kilogram meter per second. Actually, is a summation of moment about of the forces about O for a finite period of time. That is what it mean by angular impulse, right? And this is equal to the change of angular momentum of particle about O. So in order for us to quantify the effect of moment of force about O, so the author introduced what we call angular impulse. So if you calculate the angular impulse, whatever magnitude tells us the effect of that uh, forces acting on the particles. Right, I think I made mistake just now. The angular impulse is the when you multiply the moment of a single force about the origin with when we multiply that moment about O with the period of time that the force is applied. So that is the angular impulse. It's referring to a single force. Now when we consider the integration, right? So we are looking at the integration of the total angular impulse with the initial and final angular momentum of the particles, right? So we have a limits there when the force is applied is during T1 and T2 within that durations. And then we leads to equation 333a. So you can write the equation in terms of x component system, x component, y component, and z component. I just use what we have given by the Professor Miriam there. You just write for the x component. I think if you want to write the y component, you can do that as well, right? So this is the way that we can write the equations, the angular impulse momentum equations. And finally, we look at the conservation of concept here, transported property. We look at the conservation of angular momentum. So when we look at there is no total angular impulse. So the problems lead to the principle of conservation of angular momentums. In dynamics, the Professor Miriam always use the equation and translated that equation with the names, right? Here, the equation is called principle of conservation of angular momentum. I'm afraid equation 3.34 actually referring to uh, the equation called the principle of conservation of angular momentum. So these only apply when we find that the total linear impulse, total angular impulse is equal to 0. Right. I'm not going to look at example right now. We're going to look at example afterward. We're going to look at the rigid body. Um, so because we don't have much time, first we look at the chapter 6. The linear momentum equation is similar to the particle, right? So when you look at the equation 4.5 here, I'm referring to uh, the the equation referring by Professor Miriam when deriving this equation. Chapter 4 is represent a system of particle and that suit the rigid body motion, but actually this equation also shared by particles. So we have the linear momentum is equal to the average values of velocity times the mass of that body. For the rigid body, actually we are looking at the plane motion. So we just consider maybe x and y component only, right? Um, so in the figure, tells us about the local velocity at and the mass at the location is m with the subscript I. it has a velocity there, vi, and the time rate of change of position is r dot I, and we have the relative velocity of that point given by the rotational speed times the position vectors from the mass center that actually give us the